For those of you that have not been to office hours, and I'm pretty sure that includes everybody except one person. I've only had one person come to office hours yet. Now, shh, 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 shh. It's up to you what you want to do. But if I were you and you want to do really well on your exam and stuff, you just might want to head to office hours. And that's 9 o'clock to noon tomorrow in the Physical Sciences building. And are you having regular SI today too? It's gonna. Oh, okay. All right. We'll get to that. All right. So this SI schedule is going to be slightly modified today. Let's talk about the SI review. And Shai, would you like to? Um, and here's the mic.
Hi guys. So I'm having the schedule's the same, but today it's going to be extended to half an hour. It's going to be in the same place as always. It is a small classroom, so it's first come, first served basis. So if you want to be there on time, or be there early. Um, I'll have a review session up by 3 today. I just wanted to make sure I get some of the things on this lecture. So it'll be up by 3. It'll be on my Google site. I made an announcement on web courses. There's a link there that you can just go to, and it'll be like a file. I'll also have a practice exam up by tonight. Um, so yeah, so it'll be up by tonight, and then you can practice. And then if you have any questions, go to Dr. D's office hours and get those answered. Yeah, so it's gonna be 4:30 to 6 p.m. on classroom building 1, room 320. If you have any questions, that is today. Yes.
Today is Tuesday.
Any other questions?
Do you have office hours? Oh, you had. Uh, okay, are you done?
Yes.
All right. Darian would like to make an announcement. I would like Darian to make an announcement. Here she comes.
Hi guys. So I made an announcement on web courses. I don't know how many of you saw it. I also have office hours every Monday from 1 to 2 in the atrium of the Physical Sciences building. Um, you can just come to me with whatever you have. Like if you just have questions about the notes, I can just go over anything you have with lecture issues. Like I can go over the homework problems. Anything you need me to do, I'm there for it. The people who came to my office hours last semester, on their next exam after they started coming, they all went up at least a letter grade. So it's something I would definitely recommend doing because it's a lot of one-on-one and like specific issues you have I can help with. So yeah,
Okay, great. So the question.
that's all I have because my schedule is so busy. But you can always like message me on my courses too,
Yeah.
and I'll respond to you.
The question was, are there any other office hours? And the answer is no, because she's so busy. And it's normal. I only ask her to do one office hour per week, and it's actually bonus activity. But just try to squeeze it in, you know. And we'll have more office hours opportunities over the semester. Question. Physical, what the question was, what building and what room number? The physical science, let me mic myself up here, hold on a second. The location is the Physical Sciences building, which if you go, it's on the other side of campus, kind of over by like student counseling, and then there's a bus stop there, shuttle bus stop by the dorms, and then right from the bus stop you can look at my office, and she's going to be in the atrium of that building, so you'll see it. But that's next week though, and she already had that. So now, if you didn't copy down this website that Shai put together, then it's tough noogies, but all that stuff is in discussion, so you can go in there and recopy it and click it. Okay? Now, I want to encourage you and give you some tips about what to expect. And Darian can verify this. When if it's a midterm exam week, then I go into hiding after the last lecture of the week. And that's today. I don't go into hiding, but I'm really working my you-know-what off to get the exam written and then photocopied and everything. If you have a question about something, the most efficient way is for either me or Darian, or actually any of you, can contribute to a discussion post. Now, don't send me a message in the messaging service. I won't answer it. All right? Until maybe Friday, and that's too late. But Darian knows to keep, on the Wednesday before a Thursday exam, she knows to keep an eye on discussions. And I'll try to keep an eye on them too. And the reason is that if I answer your question in discussion, I'll be helping everybody else out that reads that, because they may have the same question. But if I have to go one by one, and with 500 students, over 500 students in this class, 582, something like that, it's not practical in the conversations, messaging. But discussions, very practical. But to do that, a couple things I want you to do. It's fairly simple. First of all, when you're making your discussion, you're creating your thread, use a real specific title. Don't just say, I'm stuck, or notes, or question. I have a question. Write down, some of the guts of your question. Like this one. Why was Galileo's third state of motion so important? That's my writing. So do that, and then for people that are looking at the discussion board, they'll be able to think, ooh, I need to know that too. I was wondering the same thing. But if all you do is say, help, and I don't say it, but I don't like it when students do that, okay, because it slows everybody down. So try to make things efficient. We got a big task to do on Thursday, and that'll help everybody work efficiently. The other thing that'll help things go efficiently is, you may already do this, but I would like everybody to try to remember this, even Darian and Shai. When you create a thread, make sure that you click where it says down here, allow threaded replies. And when that happens, if you don't do that, it'll just be the chronological sequence. You may be answering somebody a third of the way up, but you're all the way down at the bottom. But if it's threaded, of course, then you'll be able to reply, and you'll be able to, I'll be able to make a reply to you, and you'll be able to see that I've replied to you, and then that'll help. So it makes it a little bit more coherent and a little bit less of a mayhem madness, a steaming pile of mayhem. Question? What's the answer to that? Am I still having office hours tomorrow? What? Jacob, that's a 5-yard penalty, illegal procedure. He said no. The answer is yes. I just said it about 5 minutes ago. First thing I said this morning. All right. Now, we've got a big task to do, and I know you're all going to be really nervous. So let's get down to some discussion. We have a few things to cover before we dismiss today. And we finished with a discussion of Newton's laws of motion last time. Let's continue to talk about Newton's second law, and then we'll dip forward to Newton's third law, and that'll be the main part of the lecture, because we're really going to work our you-know-what off in Newton's third law today. But the second law, as we mentioned last time, this is the one that allows you to make a prediction of the future state of motion of a system. Remember, that's one of the basic tasks of the scientist. You know, what is going to happen a microsecond from now, or a millisecond, or a year, or a decade, or a century from now. If you can figure out, I see your question, hold on. If you can figure out some equation of motion, or the time evolution equation, as we call it, then you can do that. And this is the one that we use, F equals ma, Newton's famous second law. Question in the back. I'll talk about that at the end of class. Let's focus on this stuff, okay? Now, this is the version of Newton's second law that makes most common sense, because the numerator here is the amount of push, and everybody knows that there's a difference between Superman pushing and a little kindergartner pushing. Okay, so the numerator is clear. If Superman's pushing, you get a lot of acceleration. If a little kindergartner is pushing, it'll go, but it's just kind of pokey. Similarly, the mass in the denominator, if you have a lot of kilograms, that's like the difference between pushing a regular carton of groceries and pushing a diesel locomotive. Only Superman and Arnold and Chuck Norris can do that. Except they got these guys on like ESPN, strongest man in the world competitions. I guess they do, I don't know what they do, box cars. It's kind of amazing what those guys pull. Now, here's the basic technology that we developed early in the semester. Acceleration is the change in velocity over the change in time. That is actually a vector statement, if we want it to be a vector statement. Here's the other way of writing Newton's second law, F equals ma. And this one introduces to us a slightly different, come on down and sit somewhere. Don't stand back there. I don't mind. This allows us to put together a little bit more instructive version. F equals m times delta v over delta t. It's really F equals ma, and since a is equal to delta v over delta t, this is certainly kosher. You know, this is righteous. Okay? And the thing about it is nice is you can think about it. I like to think of stopping force. You know, like when you have a penny or a pizza that slides across the counter, if there's a lot of friction, the stopping distance and the stopping time will be small. Okay? So if you have a weak force, then that means the stopping and the same amount of speed to burn off, that means you're going to need a bigger denominator, a lot of stopping time. Okay? And so this is the one that's helpful for interpreting forces and motions, the stopping time, and so forth. So go ahead and circle that one. And the thing I like to always think about is stopping time. So if you have a longer stopping time, that means the stopping force is smaller. Okay? That means that delta t in the denominator there is bigger if it's a longer stopping time. And that means that if you're stopping 1 meter per second of motion, it's a lot less force to do it, okay, if you have a longer stopping time, okay? And I gave you the example here of box jumping. You know, one of the things that if you do plyometric workouts, you want to flex your knees a little bit when you're doing that, because if you don't flex your knees, it can be really hurtatious to your whole body. You'll get jarred every time you do it. So you flex your knees just like this guy in the picture. Another good example is stopping in a snowdrift, which is actually kind of fun if you're not going too fast, versus stopping at any speed by running into a brick wall. You know, the brick wall is really rigid, and it gives a lot of stopping force, so delta t is very small. It'll stop you like that. But a snowdrift is kind of soft, and it'll stop you, but it'll take a second to do it, and it doesn't damage your vehicle. But stopping like that with let me like that with a brick wall, you don't want to do that because it wrecks up your car. Now, some of you may, want to avoid wrecking up your car. Anyway, so that's kind of what we were talking about last time. I want to do some practice with you on Newton's second law. So get your lovely clicker going. For those of you, I'm going to start writing names down. Everybody that asked me about how their clicker works, did it work yet? And I'm going to call you out in class. So that'll be next Tuesday if it happens again. Anyways, if you're still blooping with your clicker, hold the power button down and until you get the flashing square, and then type in BB, and you'll be on my frequency, and you'll get the Go Nitro message, and then the ready sign. Now, we're going to have a calculational question here, and hopefully it'll be cinchy for you, but get your calculator out too. And definitely bring your calculator on Thursday. And yes, you may bring a graphing calculator. It's kind of overkill, but the main thing you need on Thursday is if your calculator has a square root key. So this is like the little baby calculators, that you buy for $5 at the dollar store. If it has a square root key, you can do it. So anything above that is gravy. Okay, so definitely bring that. You may not use your cell phone calculator though. Okay, so no cell phones. So if you don't have a calculator, you'll survive. Just take you an extra minute. Okay, here's your question. Calculate the weight force on Mr. Tyrannosaurus Rex. Okay. And your clicker should have started at the number 1. So make your calculation, discuss it with your neighbor, talk it over. You can't talk it over with Darian because she has to go to music class. But talk it over with your neighbor and put your number. Now I'm asking you for the nearest Newton, not the nearest tenth of a Newton, the nearest Newton, nearest whole number of newtons, just like it says up there in EG. Now, if I ask you a question like this on Thursday through the iClicker, which I cannot tell you if it's going to be on the test, but if it is on the test, you'll want to be able to do this without thinking. Okay, Ivana? So, did you click carefully? Excellent. 30 seconds. Let me try eating a little bit of my peanut butter sandwich here. Okay. Now, I want to give you, peanut butter sandwich. I want to give you some mental guidance here. If to estimate your answer, kind of mentally estimate it, where is my answer going to be, approximately, just add a 0. Because G is pretty close to 10, so if you're doing mass times mg, good old mg for the weight force, whatever the mass is times 10, so add a 0. So that means 3420. is an estimate. Now, the actual answer is going to be a little bit less than that. Okay? So I haven't closed the question, so if you want to readjust your question, your answer, you can certainly do that. Hopefully you guys are geniuses. But yeah, 3420, you should come in a little bit below that. Okay, I'm going to stop the question now. Let's take a look at what you guys have got. 342 kilogram T-Rex, which is probably a baby T-Rex. Uh-oh. We have 261 people that voted for 3352. That is the correct answer. Now, for those of you that answered 3351.6, I'm grading you correct today. That's about 36 of you. But on exam day, if you don't do it right, I'm going to mark it wrong. Okay? So be aware of that. All right, let's try another question. And this next question, hit the refresh key, kind of like these little hound dogs, because this is a multiple choice question. Number 2. The metric unit of force. Ooh, the room is quiet. Excellent. Got you right where I want you. "30 seconds. Read very carefully. And I'm glad I see bunches of people consulting with their neighbor and talking it over. That's great today, but on Thursday, of course, you got to do all your work yourself. You have to make all your decisions. But that is why we are practicing right now. 5, 4, 3, 2, 1, 0. Oh, and did I say to bring your clicker to the exam? Yes. Always bring your clicker to every class because we are going to use it. So let's... Yeah, this is pretty much the genius category here of Jeopardy. The correct answer is B. And the way to remember that is the unit of, and you might want to write this down to reinforce, the unit of the metric unit of force, the Newton, is 1 kilogram meter per second squared. So that's a bunch of kilograms, a bunch of meters, and a bunch of seconds squareds. All right. Squareds. Kilogram meter per second squared, which we talked about at the end of class last time. And so this is why we call the Newton a derived unit. In other words, you can't make a picture of a Newton. The only way that you can get a number for it is by making a calculation based on distance measurements, temporal measurements, and mass measurements. Speaking of mass, let's talk about that and reinforce that a little bit. Now, we talked about last time the law of inertia, Newton's first law, developed initially by Galileo. And what Newton developed is the idea that mass is the quantity that carries the inertia. And so that in his law, the more mass you have, the harder it is to change its dynamical state. Hence, it's in the denominator of the acceleration form of Newton's second law. All right, A equals F over M. All right, now to review the gram, that's the mass of a cubic centimeter of liquid H2O. All right, at room temperature, I think it is. So the way that this works, you use this physical device to measure the mass. You don't have a meter stick. We got that. For distance. To measure time, we have pendulums and different things. And now we have a timer on your iPod or your iPad or your iPhone or whatever you got. But for a mass, the balance is the thing to use. So what you do is you put your unknown object in there, say a basketball, and then you put a bunch of water on the other side. So a liter bottle of water would be 1 kilogram, and a basketball is less than a kilogram. So this is a righteous picture here. So if you put 1,000 grams on the left side of the scale, then the basketball is going to go up in the air a little bit, all right, because it's less than 1,000 grams. And so what you want to do is balance your object, whatever it is you're trying to measure, and then count the number of grams of water or cubic centimeters of water on the other side. So you may have to unload a few cc in this case, because a kilogram of water overbalances a basketball. Okay, so it won't be level. It'll be like this. But you unload a little bit of water, unload a little bit more, and when it evens out, then you look and see, okay, how many grams of water in there have I got? And that's the number of grams that your basketball's got, because they balance, all right? And so that's how we use a balance to figure out the mass. And that's kind of primitive. It's the old-fashioned way, but it always works. And it's a good way to think about the connection between cc's of water and figuring out the number of grams in an unknown object. So we get a big check mark over here. As soon as that thing balances, you're done. Just count the grams of water you got. And ding, that's the same number of grams of basketball that you've got. Okay, another thing I want to go over with you, and that's the directionality of acceleration and force. We've talked about this already. The net force equation, F equals ma, is a vector equation, or you can write it as a vector equation. Now, sometimes if you're just working in a one-dimensional system, you don't have to put in fancy arrows to indicate vectorness. Pluses and minuses will be enough. But if you want, if you're NASA, yeah, you have to have a vector equation. And the mass here is a scalar quantity. You just have a number of kilograms. You don't have a direction. So you never say, well, the mass of the basketball is about 640 grams northwest. You just say the mass of the basketball is 640 grams, period. All right? But the directionality of the acceleration tells you the directionality of the net force. So if you're trying to figure out who's going to win, you just look to see which way it's accelerating. If you're looking at a tug of war, and that way you know who's got the stronger team and who wins the net force battle. Same as the Dwight Howard and LeBron James example we talked about last Thursday. Now, this works with even more complex situations. So I want to take a look at this Ferrari down here and go ahead and try to sketch it. I've got mine sketched in perspective. You could do an overhead view if you want. Here's the forward axis, and here's the aft axis relative to this Ferrari. And then here's starboard axis over here to its right, or starboard. And then port is to the left. And the way that you remember that is the same number of letters in port as there are in the word left, 4 letters. Okay, now if you have, an impulse coming in at an angle here along this line alpha, if it's coming in at 45 degrees and you're moving in this direction, it's going to impart a force to you, okay? It's going to change your state of motion, all right? it's going to give you, it's coming in at 45 degrees. So let's say that's coming in, halfway between aft and the port axes. It's coming in along this axis marked alpha. Okay? And you're going to get some forward newtons out of that. Okay? But they're not going to all be forward newtons because it's not coming in from straight aft. Okay? If it came in from, that'd be like a jet getting a positive tailwind. Okay, and that'll speed you up if you're heading for Chicago in a jet. It's nice. All right, but this one's kind of coming in from the side at a diagonal. So you get a little bit of speed up. The speed will change from the forward newtons. And then the starboard newtons, which you also get a little bit from this impulse, those will change the direction. So that'll mean, you'll get budged out of your path and you'll curve off to the right, to the starboard a little bit. Okay? And so those are the two different ways that a force can change the state of motion. It can change the direction, or it can change the speed, or it can do both. All right, now, uniform circular motion, which is in Chapter 3, but we'll tackle next week, is about constantly changing motion, especially the direction of the motion, even if the even if the speed is not changing. But this is the generic situation. Any kind of a force will give you a little bit or a lot of forward or aft, a little bit or a lot of, or zero, port, starboard, newtons. Okay, it just depends on your motion at the time you are experiencing the force. All right, so that's just a little bit of reinforcement of Newton's second law. In other words, the directions are important. And you had some homework problems. By the way, Shai told me, we had a lot of students yesterday asking about problem 7. Problem 8 in homework 7. About Alafea going south and then turning west. And the question was, what is delta V? Now, there's a lovely discussion post about that in which a student asked and I answered, and I did some ASCII art, so it's all very legible and clear in discussions. Okay, so raise your hand if you've gotten my highlight notes from the textbook visible. You know what? If you're not doing that yet, you're going to miss something out because I'll probably be adding notes as I write the exam. So just so you know, that might be a good strategy to help you prepare for the exam question. How do you access the highlights? We talked about it last week. Go back to your notes, and I think it's also in discussions. All right? I'll leave it up to you guys to sort that out. Look at your lecture notes. I put it all down there last week. Okay, 3 laws of motion. Third law. Back to the third law. Action and reaction. This is the famous one. For every action, there's an equal but opposite reaction. And that means if you're, the skateboarders up here in the front, and they push off from each other, the other guy pushes back. Okay, that's the way it works. And in fact, this is the thing that Newton said was equal in that interaction. So we had, I can't remember, we had Jacob and Javier, and you guys did Jacob, you guys did you did the pushing off, right? Yeah, okay. So they did the pushing off, and the theory is that their push force was equal. One was left, one was right, yes. But theoretically, they're equal. So here's how you would state it one way in black. Whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the first force exerted on the other object. Okay, and a good example is skateboard. As a matter of fact, that skateboard interaction is lovely because an enormous amount of physics from the level of Newtonian physics, galaxies and comets and planets and stuff, all the way down to the atom can be modeled as an interaction similar to the skateboard interaction. This is the actual way that Sir Isaac Newton wrote it. An object that exerts a force on another object also experiences an equal force from that other object, but in the opposite direction. And note to students, this is from page 40 uno in the textbook, the e-text. All right, so the forces are equal but opposite. The effect is an acceleration in whatever direction you're getting a force. Okay, so now discounting the little bit of friction that they encountered from the surface of this carpet, the only force acting on those two guys was their interaction force, and then there's gravity, weight force, and then the floor pushing upward with the same amount of force to keep them on the level. And so the only thing that was unbalanced was the push force. So that was the net force on each of those guys. Now, I want to take a look at this football player. So make a note. Let's see, who was this guy? This is Weaver from a couple years ago. Now, this guy, when he's running, and if you've ever been on a track team, you're in a sprint event, hopefully your coach told you that your sprint motions should be like throwing your foot or throwing the track behind you. Just like a football player or a pitcher throws the ball forward, a sprinter is going to try to throw the track behind him. So if you look at his foot, here it is. He's pushing down and behind him. Okay, that's the way he's got his traction. He's got his cleats. They're dug into the turf, and he's getting a little traction. And in this particular photo, that is the direction that he's going. Now, in lieu of Newton's second and third law specifically, here's the force, here's the pushback force from the surface of the field. Okay? And that's going up and forward. And so that is what is actually pushing him. He's trying to push the field. And the field is locked up to the planet Earth, and it ain't going nowhere. All right, so he's moving the Earth, accelerating the Earth, but it's worse than a drop in the ocean. But he's getting an acceleration from the Earth in the up and forward direction. So he's pushing down, he's digging his foot into the turf, and he's digging it backwards too, and he is propelled. So it's not him. It's not his force. Isn't that weird? It's the field that causes him to move so fast. He's not doing nothing. He's just stimulating the beneficial effects of the field, and away he goes. All right. Now, a couple things about this, and this is related to the bowl of cherries concept in the homework. And Agent Smith trying to get that bowl of cherries from Justin Bieber's BFF. Okay, this whole scenario with the running back, it would not work on a field made of Jell-O. All right? Because the Jell-O is not rigid. So if you want to get some pushback, you've got to have some rigidity. In other words, and I explain this in the textbook, that the actual rigidity of the drag strip in the textbook is the rigidity of the silicon and hydrogen and calcium atoms that are all bound in the concrete. And they basically act like little trampolines that flex downward but give a net upward force for a horizontal racetrack. So you can think of a million other examples of third law in action. Now here's one that you may not have thought about. The earth and the moon. And this is in the textbook. This is in chapter 3 towards the end. There's a picture of the earth and the moon drawn to scale for distance and diameter. and they interact gravitationally. Now, it's not a push for a certain amount of time, it's a continual gravitational interaction. So they're exchanging an interaction, and the amount of force that Earth exerts on the moon, 73 skillion newtons, because the Earth is pretty big and the moon is pretty big, is the same number of newtons that the moon exerts on the Earth. So actually the moon is orbiting the Earth, but the Earth is on a gravitational orbit as well. Now, the Earth is so massive compared to the moon that it doesn't really move around, but we can measure it. We can measure Earth's gravitational, it's doing a little circular dance. The moon's doing a big circular dance. Once every 28 days or whatever it is, 27.35 or something. It does one circular lap around the Earth because of that gravitational interaction. But theoretically, the newtons that they're experiencing in that mutual gravitational interaction, which we'll also talk about next week, is equal but opposite directions. And those are circular. The moon is pretty close to a circular orbit. And so we'll be talking about that next week on Tuesday when we talk about the Nardo ring and the circular motion concepts at the end of chapter 3 of the textbook. Now, at the beginning of chapter 4 is a discussion of two skateboarders. And we're going to work this out. This is page 45. If you looked at my highlights, you know that you've known for a couple days that I was going to be shooting for this in today's lecture. So let's let this be our deluxe worked out example of pretty much everything. Newton's third law, Newton's second law, delta V, acceleration, all that stuff. The only thing we won't be doing is figuring out positions on this example, but you could figure out positions and stuff. Okay, so now this is an example of two hypothetical skateboarders. Let's look at the first one, Carl. His mass is 40 kilograms, 40.0 kilograms. And we're going to say that Carl is at rest. Okay, so that's like the two skateboarders, Jacob and Javier, up here. They started at rest. Okay, then they pushed off. Okay, so this is the initial condition, VI equals 0. And they have an initial position as well, but we're not going to calculate positions. If I did want to calculate a final position, I'd need to know his position on the x-axis. And his particular property is his mass, is inertia. Now, Bob, the second skateboarder, twice as heavy. So this is like a high schooler versus a third grader maybe. Okay? And he's got 80 kilograms, and his initial speed is 0. All right? So this is kind of a little bit different because Javier and... Hold on, my phone. Put it on stun. Javier and Jacob were pretty close to the same mass. Okay? But I want these two guys to be definitely different. So one of them is twice as heavy. Their interaction, let's get the specs on that. All right. Let's say that they push each other with 500 newtons of push force. And that's not a lot. That's like holding up a 50 kilogram mass. A 50 kilogram mass would be 490 newtons of gravitational force. And 50 kilograms, that's about 110 pounds maybe. You could hold up, you could hold it, maybe budge it off the floor. And some of us can lift it over our heads, a military press, or twice that much. So it's not that big of a force. All right, so let's say that Bob pushes on Carl. B on C is the subscript there. FB on C, the force of Bob on Carl, is 500 newtons. So Carl is getting 500 newtons from Bob, 500 newtons to the right. It's a positive. And let's say that Carl pushes on Bob the exact opposite direction. Negative, leftward. Okay, negative 500 newtons. Right, so there's my interaction size. That's the size of my push force. And you could get a little third or fourth grader to do that, and definitely a high schooler. All right, so this is not too bodacious. All right, let's say that their interaction time is less than a second. 0.48 seconds, delta t, the interaction time. And hey, you guys, this is the amount of time in which that force acts. Okay, so after they break contact, they're no longer interacting, theoretically. And this is the amount of time in which the velocity state will change. They're experiencing some force, one experiencing some leftward force, the other guy some rightward force, okay, but only for 0.48 of a second. So now let's figure out accelerations here. This is applying F. So number 4, this is applying F equals ma, and actually we're applying A equals F over m. So for Carl, the acceleration of Carl, A subscript c, is the force on Carl, from Bob on Carl, 500 newtons, divided by the mass of Carl, which is 40 kilograms. Okay? And so that works out to 12.5 meters per second squared of acceleration. This is F net divided by mass. A equals F over m. In other words, Newton's second law configured for your acceleration. Similarly, Bob has an acceleration A subscript b that is his net force, and the force of Carl on Bob is negative 500 newtons. In other words, 500 newtons to the left. And the divisor is the mass of Bob, which is 80 kilograms. That's from item 2, part A, his mass. And so this is kind of an idealized example. Everybody's starting from rest. The masses are exactly double of, one's the double of the other. And we're using nice round numbers. In reality, you might have, kind of scraggly looking numbers, but it would work the same way. All right, so for this one, Bob's acceleration, A subscript b, is negative 6.25 meters per second squared. Now, what do you notice about those? What do you notice about those two accelerations? They're one's bigger than the other, one's half of the other. Okay, so I thought every action was equal and opposite. Are these opposite? Yes. No. What's your answer? No, I don't want a question. I want an answer. Are they opposite? Yes. If you answer yes, you have to tell me why. Raise your hand if you answer yes, and you can tell me why. Why? All right, lovely. You can tell by looking, one of them's positive, one of them's negative. That is how we indicate opposite directions. Okay? Equal and opposite indeed. Well, the forces are equal, but I don't think these accelerations are equal. Maybe the delta v's will be equal. Let's take a look at delta v. All right, we have the acceleration from F equals ma, and we have the interaction time, which I measured. I made it up, but we'll pretend that we measured the contact time, that they were, pushing each other off. 0.48 seconds, 0.48 seconds. And so we can figure out the delta v. It's just the acceleration, whatever it happens to be, times the interaction time. All right, now this is the opposite of stopping. Okay, if you're stopping, your delta V is negative, and well, if you're going forward, if you're moving forward at a positive speed, 5 meters per second, and you stop, your delta V is negative 5 meters per second. So you have to have a backwards acceleration to do that. But this is similar to a stopping problem, except this is starting from rest and accelerating. So we're gaining speed. Here's what Carl gains. Delta V for Carl is positive 12.5 meters per second squared. Carl's acceleration times the interaction time. Now, once he breaks contact, that's it. So for 0.48 seconds, he's getting some newtons, 500 newtons. And as a result of that, the change in his velocity is rightward 6 meters per second, 6.00 meters per second. All right, now Bob is getting a negative 6.25 meters per second squared for his acceleration. And so it's a little bit different for him, but he does have the same interaction time. Okay, so let's figure out his delta V for Bob. It's Bob's acceleration, negative 6.25 meters per second squared, times the interaction time, 0.48 seconds. Now that works out to be negative 3.0 meters per second. In other words, he was at rest, but now he's going off to the left at 3.0 meters per second. All right? So that's all right. Now, does that make sense to you? Hey, wait a minute now. They're equal but opposite reaction, but those delta V's, they're not equal. So we got, okay, the forces are equal. That we got. But these other things, we're not, it's a little bit mysterious. But we can't argue this is the way it works. Okay, final velocity states. Let's figure out his final V, VF. VF for Carl, VF for Bob. What about Bob? Okay, so final velocity state, Carl. He started at 0, he gained 6, so his final velocity, V subscript F, is 6.00 meters per second. All right, so we've used some initial conditions here and some initial mass measurements, and we figured out the final state of motion for Carl. Now we can do the same thing for Bob. Bob's is a little bit different. He started with 0 and he got 3 leftward. Excuse me. 3 off here to the left. All right, so that's all he's got. And again, we're looking okay over here for interaction forces, but that's the way we set it up. But the things that we can actually measure, the accelerations, delta V, final V, those are all different. So make a note in your notes. Don't put a frown face though, just put a big question mark. Because you can put a smile face if you put a question mark over the top of it. Okay, why? Why are those different? So in other words, go ahead and write this question down. It's a good one. If their interaction forces are equal and Newton's third law is valid, and which we believe, then why aren't their final velocity states equal? Are you prepared to answer that? I hope you are, and if you're not, I want you to. Oh, you want to go back to the question? You're copying it down? Good. Copy it down. I want you to copy it down. I see some guy over here taking a picture with his iPhone. It's all on the video. It's all right. You can get it off the video. And here's the point. I won't be using the clicker for that question today. But if you, I should say, however, if you want to be ready on Thursday, like this little bee, make sure you study like this little bee and think about Carl and Bob. Now, because I'll be asking you about you know what? I might even give you all the same specs. And I won't ask you to calculate them all out. I may give you the entire spec sheet that we just kind of worked out, like on the cover page, and then ask you some questions. I might do that. So I'll be asking about, especially this last question, if their interaction forces are equal, and if Newton's third law is valid, then why aren't their final velocity states equal? Big, big question. This concludes the material that we will have for exam 1. So let's do a summary. Let's talk about where we are, and what I will be looking at. Now, I just have one item here. First law, how did Galileo develop it? We talked about Galileo a lot. So you're going to have 50 questions, 50 items, 50 points. You'll have an hour for your test. And so you can bet there's going to be a bunch of questions on this. All right? Now, when you're going through your notes and stuff, I want you to think, now what kind of question has Dr. B asked about this or like this in class and on homework? And secondly, you can ask yourself, what kind of question like this could Dr. B ask on the exam that is, 90 degrees away or, above or below the questions that I had on clickers and on homework and that we talked about in lecture. Right? So Galileo is an important guy for us, and so expect a lot of Galileo related questions. Question?
Will you ask us who developed this theory, in regards
There's a student in the second row asking me, will I ask a question about I'm not going to tell you what the questions are going to be. I'm just telling you where to study. I'm not going to say the questions. As a matter of fact, I don't even know the questions because I haven't written the test yet. I always wait till after the last exam. So between 1:15 today, after my noon lecture, and 10:30 on Thursday, I'm going to be working like a subhuman maniac to get you guys a good exam, okay? But I'm not going to tell you the exam questions now. But I am going to tell you the kind of things that if you think about them and study, especially if you think with a friend, a study partner, that on exam day you'll be happy. Okay, so this is the first thing. Second thing, second law. You know, the whole thing that we're shooting for here in the first part of the lecture is Newton's three laws of motions. That is our basic stepping stone for everything else we do this semester. And we've got them on the board now. All right, second law, all about accelerations and forces. And there's zillions, possibly even bozillions of questions that I could ask about Newton's second law. Third law. Oh, baby. This is the one where you really have to think. Skateboarder interaction. Here's another one. Here's another great question. The football player. You know? I had a classmate in grad school named Nick Pinto, a good guy. And he was about 3 years ahead of me, so he did his PhD thesis, several years ahead of me. And then, when you write your thesis, you have to defend it in front of this big committee of, 5 or 6 professors, and your defense is like for 2 hours. You write your thesis, and then you give it to them for a week or 2 weeks or whatever, and then you have a meeting, and you go up and you defend it. And they can pepper you up with any question they want, not just what you wrote about. So he was writing about some kind of solid state physics thing with silicon and gallium and everything. But after he successfully defended his actual thesis, they opened up the session for any general questions. And so they can ask a free fall question, or they can ask something about electromagnetism. So one of the professors was in this meeting. I'll never forget. He told us about this. He was in this meeting drinking a can of soda pop and going through the thesis with this guy. He wasn't the thesis advisor. He was one of the other committee members. And he's drinking his Pepsi. And he was done with his Pepsi. They opened it up to general questions. And so Nick Pinto's up there. When you're doing this, you're exhausted. I mean, it's a lot of adrenaline. So Nick Pinto's up there. They're done with that. But he was the professor put his can of Pepsi up on the overhead projector. They were using an overhead projector for slides and stuff. He put it up on the overhead projector and said, "Nick, what are the forces acting on that can of Pepsi?" And Nick was, he was all into this quantum mechanics stuff, So backing up all the way to, Physics 1 when he was a sophomore in college, it was like going in a time machine for him. And so the way that we heard at the tale it was told was Nick kind of looked at him and hesitated. And that was all the professor needed, because he then started peppering Nick with questions. Well, what about this and what about that? And by the time it was over, Nick didn't know which way it was up. He was, but they passed him. Nick won. He got his PhD. And so when I wrote my PhD, I made sure I had that same professor on my committee. But he didn't try that trick, but I was ready for him. Anyways, third law. Enormous amount of questions. And the point of that Nick Pinto story is, if I were to give you a multiple choice test about the third law, you would have difficulty, and so would all the grad students over in the physics department. And I say that as a compliment to you guys, for you to see that your degree of intelligence is equal to the degree of the intelligence of those guys. You are struggling and working with concepts that I can make those guys, cry for their mama with a test if I wanted to. Now, I'm not going to make you guys cry for well, it might feel like that on Thursday. but it's not by design to drive you around the bend. But this particular topic, yeah, there's a lot to say about it. And conversely, there's a lot to write about it and a lot of questions to ask about it. So be ready. I say to one, I say to all, be ready. Yeah. Here I am. I'm giving this inspiring story about Newton's third law. What color Scantron do we need? Nice. The answer to that is the raspberry colored one. It has a UCF logo on it. Okay, the stuff that you're going to need to know about positions, distance, time interval. So this is like our formula and equation technology. Velocity, delta V concepts, velocity and delta V formulas. All these things go into the first three items. This also goes into the first three items, accelerations and delta V over delta T. You know, all our definitions and formulas and concepts for accelerations, velocities, positions, times, and mass, all those things we need to know. You've got to have those ready to go. So I might ask you, calculate an average speed. Kind of like I think we had a marathon question on the homework like the first week. If a marathoner runs 5 miles an hour for 2 hours, how far does he run? 10 miles. But the thing is, it can get really challenging as well. Free fall calculations, we've done some of those, simple ones. And we did some deluxe ones. Okay, and the deluxe ones being the ones where you have to keep count of your minus signs for downward and plus signs for upward. Okay, that's fair game. And all of these, item 4 here, A, B, C, and D, all of those feed into item 1, item 2, and item 3. Okay, so those are the basic tools that allowed us to make our power tools. Newton's 3 laws are like power tools. If you have these basic tools down here, you can make a power tool. First law, second law, and third law. Okay, we're going to skip the Nardo ring in chapter 3. Okay, we'll save that for next week. But we'll dip forward, you just read a page or so forward into chapter 4, where especially where I talk about the skateboarders, because I work out the skateboard examples at the beginning of chapter 4, using accelerations and forces, and using another method that we're going to talk about next week. But the left-hand side of the page, I believe it is, in chapter 4 with the skateboarders, that's the side that we're going to focus on. That's the side that we worked out in class today. Now, let me just verbally, it's not on the slide, but verbally remind you, be here on time. You'll have 60 minutes. So we won't have to start exactly at the dot like my Monday, Wednesday, Friday classes. But Thursday, be here on time. Oh, you guys are already 1 foot out the door. I see somebody getting ready to go. If you miss out on this, you're going to slow everybody down, and everybody's not going to like that. Bring a raspberry colored Scantron, the one that has the UCF Pegasus logo. The brown ones from the School of Business are no good. Okay, only the raspberry colored ones. Question? The question is it the same as the pink one that you can get at USGA? And the answer to that is no, it's raspberry. It's not pink, it's raspberry. But yes, that's the one that they have up there. I guess they give them for free, right? We're not done. I know you guys like to dismiss early, but this is important stuff now. bring a pencil for bubbling in your Scantron, because most of the tests will be Scantron. So you might have like 42 questions on Scantron, and then a bunch of questions for 8 points on the clicker. Okay, so it'll be a double, two-mode test. Bring a good eraser. So like those pink rectangular jobs from third grade. Because if you blow it on the Scantron, we had this last fall, they had a new scanner for the Scantron, and it was so sensitive that if you didn't really, really, really erase it well, it counted as 2 dots. If you write in the answer, erase it, and then put in a different answer, it'll count your erasure as a dot, and then you get it wrong. Okay, so you don't want to do that. But one of those little pink erasers from third grade is good, not the one that you had in third grade, but go out and get another one. Those should be good. Calculator. Scientific calculator is fine. Anything with a square root. You may not use your cell phone calculator. Anything with a square root is fine. If you forget your calculator, I'm not going to have one for you, but you'll just do it by hand, and there'll be plenty of time. You'll just have to do some 6th grade long division or whatnot. Okay? Question. Graphing calculator, yes, is fine. I already talked about that. Question. Do we need a green book? No. And let me repeat what I said last week, I think, or 2 weeks ago. Your exam, when you look at it, you're going to leave it face down until I say to begin. You're going to have a cover page. And on that, you'll write your name and PID, at the top. And then there'll be a big admonition not to open the test, etc. And then at the bottom, there'll be maybe some diagrams, maybe some numbers, maybe the Pythagorean theorem, a few things that I give you for free. And then the next page will be your matching. Now remember, the matching is where the formulas come in. So you'll have a formula and a set of concepts that you have to select. A, B, C, D, or E from the concepts for each of the formulas. Okay? And that's equivalent to a formula sheet, but you get 1 point for each one of those you get right. So you don't have to memorize the formulas. Do not spend time memorizing. If you do, you're going to be not using your time to the best efficiency. The best thing to do is to go to SI, review, and then study with a friend. That is absolutely the best. Memorizing, no cards, is maybe going to help you for one question, maybe, if that. Clicker. Make sure it works. And make sure, by God, that it's registered. All right? There's still a few of you that aren't registered and aren't clicking. If you're not registered by Thursday, God bless you, you ain't going to get any points. In class, it's one thing because you only have to have 85%. But you have to get everything. If you're not registered through web courses for Thursday's exam, that's possibly 8 or 10 points you ain't going to get because you're not registered. And all you got to do is register in web courses. Question? Are we going to be able to write on the test or have scratch paper? The answer is yes. There'll be some scratch work areas usually on the test. Like sometimes the last page is blank, and you can write on it, and you'll be turning it in, but your name will be on it. But yes, you can write on it, so don't worry about that. There'll be plenty. So don't worry about scratch paper. Pencil, eraser, calculator, clicker, brain. All right. There'll be a small homework number 8 for you by supper time. And I highly suggest that you read very carefully in the e-text and especially figure out how to look at my highlights. You're dismissed. Are you? discussions. People are doing it. Actually, you know who you can email is Darian. Have you been able to get to my highlights? Lord of mercy. Okay, discussions, or text Darian, or post something. Darian actually has contributed in discussion, so read that first, and if necessary, start another thread. Okay.
Like, what if we have SAS?
And the reason is, I, yo, the reason is I can't see things the way that you guys do because I have the teacher version and it doesn't work the same way you guys do. But Darian has it, and so, all right.
If we have SAS, we're not really going to be in the classrooms.
Yeah. So what you're gonna do now? What's your name again?
Joanna Hidalgo.
Joanne.
Joanna Hidalgo.
Okay. You're going to be taking it over at SAS. Okay. And just report there at the beginning of lecture. And the clicker questions, you'll just write them out on the paper.
Okay, so
And I'll grade them by hand.
Okay.
But you'll do the Scantron part just like everybody else, and we'll grade that through the computer.
Okay.
It works out good, and you'll have double time and all that stuff. So,